What does the center of mass have to do with balance? Well, the simple answer to that is it turns out the center of mass is the balance point, and that's something we'll be able to show in a future chapter when we develop a little bit more physics surrounding like how systems are maybe out of balance, which usually tends to mean that they're going to rotate in some way when they're out of balance. Um, but I want to bring it up now because I want to make sure that we understand that we're talking about center of mass because of this relationship to balance. So that's again part of the reason here. I also want to mention though, like it's a little weird. You might say like, well, why are we doing it in this chapter if all the stuff on balance is more in a later chapter? And I agree, it is a little bit weird. Most modern textbooks still have center of mass in this chapter because it turns out there is a deep connection between center of mass and collisions. And when I look at the examples in the topic on collisions, which is the next topic after this one, um, I'm going to be tying back in some examples so that we'll be able to see a little bit that the center of mass is relevant to that. It turns out maybe the original inspiration for that was the Feynman lectures, where Feynman really kind of used symmetry arguments and looking at center of mass frame of motion to be able to do all kinds of complicated, even collision processes and analyze them. And that was for both one dimension and two dimension. In this class, we're going to mostly look at one dimension. We might have one or two sort of in two dimensions, but it turns out the math has a propensity to explode quite a bit. So we're going to try not to get too mathematically explosive because definitely it gets gnarly. Anyways, but there is this deep connection. But I think as time has gone by, like textbooks have often kind of tended to keep this topic in the momentum chapter, but the way they present the material it's become less clear, I feel like, at least when you look at the examples they do and how they discuss things, what the tie-in really is between center of mass and collision. So you'll hopefully catch a glimpse of that looking at those later examples. But getting back to this question though, like I said, the reason we're going to need it after this chapter is again in relation to balance. So like maybe as a quick example, like if I look at a person, look at some examples here of a person. So like let's say I draw kind of a stick figure person here that's standing on this ground here, or maybe he's floating above it, I don't know. Obviously if his feet are here on the ground, this person looks like they're pretty well in balance there. But like let's say the person has shifted their weight a bit and they're really like putting most of their weight sort of onto like one leg and not so much the other, right? So that might look something like this. So here you could say their center of mass point, which usually for most human beings, center of mass point is somewhere like maybe a little bit below navel level, somewhere in the torso. So that could be the center of mass point right there, is clearly between the person's feet. In other words, it's right above their support base. But if they shift their weight to the point where they're maybe just to the tipping point, right? The tipping point really would correspond to the point where their center of mass is just getting to the edge of their support base, right? And the person is more clearly out of balance, like if they're like this, right? And, you know, maybe their one leg is here and the other one is like already filling up in the air or whatever. This person is more clearly out of balance. Their center of mass point is not above their base of support. And unless they do something to catch themselves, they're going to rotate out of balance and maybe hit the floor somewhere down here. Hopefully that doesn't happen because it looks painful. You know, a similar example to this, I mean, this is with two legs, right? But, you know, there are some birds, right, that can stand on one leg. So, like, let's say I've got, like, a bird maybe sitting on maybe this is a branch or something like that. And I'm just going to model the bird as, like, a kind of point mass, or maybe it's like a little ball that represents a bird here, right? But the way that they can balance on one leg is as long as they make sure their center of mass is right over that leg, they're going to remain balanced. It turns out you can extend this, though, to hanging objects, right? So if I have, let's say I've got a rod here, okay, and it has two masses hanging from it. And you could see something like this maybe in like a mobile sculpture, right? But if you have one mass that is larger than the other mass, then the point where you'd want to support this rod so that it is in balance is going to be a little bit closer towards the larger mass, right? And that's going to correspond to the center of mass point of these two hanging masses on that object. And there maybe are other examples of this, like, many mobile sculptures have multiple kind of like stages, I guess. But at each point where it's hanging in balance, the total weight hanging off one side versus the other side, if you calculate the center of mass of that, that would be the point where it's going to be supported if it's supposed to hang in balance. There's a lab that I commonly do where we're going to look at, like, we're going to have like a meter stick like this, right? It's not really drawn to scale here. But like, let's say I support that meter stick at 2 points, and then I hang some mass off of it off to one side. Well, how far out can you put this mass before the meter stick starts to tip? And it turns out the answer to that has to do with the fact that, like, hey, if this is the center of mass point for this mass that's hanging from the meter stick and the meter stick itself modeled as a point mass, right? The meter stick itself might be, like modeled as a point mass somewhere near the center. Maybe if it really is a true meter stick, it might be somewhere near the 50 centimeter mark, right? But when I pull this mass that's hanging from it far enough out, the meter stick will tip once the center of mass is outside this support base. So again, that's kind of like this balance principle and how center of mass relates to it. So let's check out the answer here. It says the center of mass point must be above the base of support. For a hanging object, the center of mass must be between the points that object is hung at, or directly in line with where it hangs if there is only one line of support.